Welcome. In this video, we continue our discussion of image formation by lenses. We are primarily interested in two subjects. The first one is magnification, and the second one is going to be related to the different types of images formed by different lenses in different contexts. And maybe just to prime us, the idea of magnification is related to the size of the image formed by a lens relative to the size of the object. So before we get into these 2 points, it's worth connecting this section to our previous section. So we will look at the ray tracing rules in the context of a convex lens. So remember that when we have a convex lens, and particularly a thin lens, I should remind you that a thin lens is a lens which by virtue of its thickness prevents chromatic aberration or dispersion. So now if we have an image, an object that is in front of such a lens, we have ray tracing rules that enable us to get an idea of where the image is going to be and how the image is going to be formed. And this is at a qualitative level. Although there are many rays that we could focus on, we primarily focus on these 3 that are indicated here. So suppose the purple line here represents our object. Notice the arrow is upright. So this arrow, purple arrow, represents our, blue arrow, I should say. The purple is the image. Our blue arrow represents the object. It could be a person, it could be a bug, it could be a vehicle, whatever object you can imagine. And we know that light always scatters, or we think of it as light rays are always divergent from a point. At least that's what electromagnetic laws tell us. So if we are to focus on this point and take into account the 3 rays that issue from this point, of course I should say again, many rays, some of them are scattered this way and that way, but we mainly focus on these 3 relative to the lens. And the first one is the one that is initially parallel to the principal axis line. So it enters the lens parallel, and when it exits the lens, it exits so that its direction is changed, and it's now headed toward the focal point of our lens. So this is the first ray. It's the one that enters parallel into the lens and exits so that its new direction is toward the focal point. It will pass through the focal point. And then the second ray, which is very important, is the one that passes through the center of the lens. This light ray propagates from the source, from the object itself, through the lens with its direction unaltered. That's very important. The light rays that pass through the center of the lens are not altered in their direction of propagation. So we have these 2. Actually, these 2 light rays are all we need for us to get an idea. But for the sake of to get an idea of where the image is going to be located, and furthermore, what does it look like? What does the image look like? But for the sake of completeness, we also take into account the 3rd light ray. There are situations where we will not be able to plot this light ray, but in this case we're able to, so we will include it. So this is the 3rd light ray. It's the one that is initially directed toward the focal point of the lens on the side of the object. Notice the object is located on this side, and this light ray is initially directed toward the focal point of the lens, and it enters the lens so that, it passes through the focal point and then enters the lens. But the key is that due to Snell's law, it gets refracted so that now it exits the lens and is now parallel to the principal axis. Now, where these three light rays converge, where they meet, is where the image would be located. In other words, this point of the object will be located on this side of the image. If this were someone's head, then in the image, the head would be located on this side. Suppose we were to also do the same for another point. Suppose the torso of the person, if this were a person, then the torso will also be located here. We would be able to draw, again, these three light rays for the torso. And the point here is that we would be able to recover the image of such an object. A couple of things that are important here is, the first one is the focal point. And notice, because we have a convex lens, we have a focal point here, a focal point there, and both sides of the lens have the same radius of curvature, so the same focal length. In other words, this is the focal length, script F, and the same would be true on this side. This distance from the middle of the lens, from the center of the lens to the focal point, that will be the focal length. And remember, because this is a convex lens, the focal point is thought of as being positive. And another point of note, which we have highlighted before, but it's worth emphasizing again, are these two distances. The first one, this is the distance from the center of the lens to the object which we are trying to image. This distance is signified by D0 or DO, DO meaning distance to object or distance of the object. And then the other distance is the one from the center of the lens to the location of our image. And this is signified by DI, again, distance of image. These are the pieces of information we have highlighted previously. There are two which we purposefully overlooked for the sake of introduction. And the first one is the dimension of our object. In other words, how high or how tall is our object. This is usually signified by H0 or HO, the height of the object. And the other one is over here, HI. This is the height of our image. This should already begin to give you an idea of where the idea of magnification is going to come in. Remember, magnification, as briefly mentioned in the beginning, was the size of the image relative to the size of the object. Okay, so now let's talk about the relationship that we had between all these parameters, these distances. We know that the reciprocal of the object distance plus the reciprocal of the image distance is equal to the reciprocal of the focal length. This is what we called earlier a thin lens equation. This is true for lenses and also for spherical mirrors. Although we will not talk about spherical mirrors, but this relation also holds for them. But now, these parameters which we neglected earlier are now, we need to talk about them. How do they enter the scene? Well, remember, magnification is related to the size of the image relative to the size of the object itself. Well, the size of our image in the context of a convex lens is HI, that is the height of our image, and the size of our object is HO, which is over here. So the ratio of these two, that is the height of the image divided by the height of the object, this gives us the magnification of this lens. If this ratio were 2, what this would mean for us is that the size of the image is twice that of the object. Hence, this lens would be functioning as a magnifying glass. So it makes the image to look larger than the object. However, if it were doing the opposite, suppose the size of the image were, let's say, a half that of the object, that would mean the lens is basically shrinking. It's shrinking the image, so the image is smaller than the object. We will get into the details of all of this. But one of the important things we need to note about convex lenses is that, or maybe I should say about lenses, is that sometimes the image may change the orientation. Remember, if this were a person, if this object were a person, and the top of the arrow represented the head of the person, notice the head of this arrow on the image side would be at the bottom. So notice the image is inverted relative to the object. So this lens would produce an image that's upside down. And because of this, we think of, we can talk about the effect of the lens as being inverting or keeping the image upright. So the lens can do two things. It could either keep the orientation of the image. That's one thing it can do. It can affect the orientation. And the other one is it can affect the size of the image. So those are the two things that a lens is capable of. It can affect the size and it can affect the orientation of the image produced. Okay, so over here you might notice that M is equal to HI over HO. It is also true that the magnification of a lens is also equal to negative the image distance divided by the object distance. Do not worry about the negative for now. We will talk about it later. But if this equality of the image distance divided by the object distance comes from arguments from congruency. The idea is that these triangles here are actually, it's possible to argue that they are congruent to one another. In other words, then this side will be related to this side, and this side is going to be related to this side. When I say, I mean this image distance is related to this object distance. But that's beyond the scope of our discussion. The point is, when the dust settles of all those congruency arguments, one of the equalities is that magnification is also defined as minus di, that is the image distance, divided by do, that is the object distance. Okay. Now, when the magnification is negative, that is, it's less than 0, this means our lens inverts the image. It inverts the image. So, let's take, for example, if the height of the object here is HO, HO is upright. But the fact that the image produced by such a lens, now notice HI is on the bottom side of the principal axis. Therefore, we can think of HI as being negative. Because HI is negative, this means M, so let's quickly do this. Because HI is negative, let's say HI is some negative number, let's say minus 2 centimeters. Let's say 2 centimeters, and let's say our object was initially, 4 centimeters. So our object height, this is just an example, an on-the-fly example. So if our object height was 4 centimeters, and it produces an image whose height is 2 centimeters, but notice the image is going to be on the bottom side of the principal axis. Therefore, we need to say that HI must be negative. So we say HI is negative, and what we will learn here is that the magnification of such a lens in this particular example is going to be minus a half. I'm sorry, minus a half, I wrote a quarter, minus a half, minus a half. So notice what we have learned. We have learned that the sign of the magnification is negative, and that teaches us that this lens inverts the image. That is, the orientation of the image is opposite to that of the object. Moreover, the number here is smaller than 1. So that means the object, the image, the height of the image is smaller than that of the object. So this lens would be a lens that shrinks the object. In other words, the image of the image is going to be smaller than the size of the object. Okay, so this is just an impromptu example to convey the idea of what we mean by magnification. Magnification tells us about the orientation of the image relative to the object and also the size of the image relative to the object. Of course, the other situation we could possibly have is if the magnification is positive, that means our image is going to be upright. And clearly that's not true for this particular case, because notice our image is on the bottom side of the principal axis. We will talk about a case where the image is upright. Maybe I should mention it now. Convex lenses can produce two kinds of images. And in general, lenses can produce two kinds of images. The first one is the first one is what is known as a real image. And the second kind is known as a virtual image. This is just to prime you for what we're about to for what we're about to discuss, but don't be concerned about it. Let's get into it. Okay. Now, we're ready to talk about the different types of images that can be produced by lenses. And I've classified them into three. Some people call them case 1, case 2, case 3. I've called them type 1. It's just different naming, but the idea, the principles are the same. So the first type of image is one that is formed by a convex thin lens. Remember, we're going to stick to thin lenses, so no aberration and no dispersion. Okay, so type 1 image is one that is formed by a convex lens. Because we're dealing with a convex lens, our conventions suggest, or they instruct us, that the focal length must be positive, larger than 0. And such an image is produced when the object we are imaging, here's our object, is further than the focal length from the lens. So what is the focal length of this lens? Well, the focal length is only up to there, but the object is located further away from the lens than the focal length. So D0 is larger than script F. In such a situation, the image which is formed is known as real. It's a real image. What do we mean by real? We say that the image is real because such an image can be projected onto a screen. That is, if we were to put some kind of a screen here, we would actually see this object. We would see the image of this object. And we also mean that the light rays actually pass through that point. That's why it's real. There's actual light rays, physical light rays that actually pass through this point in space-time. Don't be concerned too much by what that means. When we talk about the different types of images, the other kind, you will see what I mean by the light rays actually pass through this point. Okay, so a convex lens where the object is further from the lens than the focal length will produce what is known as a real image. Moreover, the image produced by such a lens and such a condition will be located on the other side of the lens. This is very important. Notice the object is on one side and the image is on another side. So the point is, the two are not on the same side. Hence, the object distance is larger than 0. And if you were to go back to the definition of magnification, if this is the situation, that is di is positive and do is also positive, this means if di is positive and do is positive, this means our magnification is going to be negative. And what do we know about negative magnification? This corresponds to inverted images. Hence, a lens, a convex lens, where the object is further than the focal point from the lens, will always produce an inverted real image on the other side of the lens. Okay, so let's consider a picture that is, we've spent a lot of time on this picture, so I think this should be sufficient. Let's consider another case. This case will help us appreciate what we have written here. By contrast, I hope by contrast we will have a better appreciation of this. Okay, the other situation is where our object is no longer further than the focal point from the lens, but now it's closer than the focal length to the lens. The focal point of the lens is here, and our object is located closer than the focal point. Well, then let's follow the ray tracing rules. The ray tracing rules are, we are to locate a point of interest, which in this case is going to be the top point. Three rays can be drawn, although in this situation only two can really be drawn. The first one is the one that enters the lens parallel. Remember, this light ray will emerge from the lens so that it's pointed toward the focal point on the other side of the lens. So there's our light ray, the first one. The second one is the one that passes through the middle of the lens with its direction unaltered. So there it is. Notice these two light rays actually will never meet. They will never meet. However, they do propagate as though they came from the same point. In other words, if we were to extrapolate their paths, they actually seem to have come from one source, from one singular point. And that singular point actually will be where the image is going to be located. I repeat, these dotted lines are an extrapolation. They are not actual light rays, but they're an extrapolation of these two light rays. When we observe how these two light rays propagate, it seems as though they came from one singular point. If we play that backward, we extrapolate back, we find that the point where they converge actually would be the point where the image is going to be located. Now, because these are not real, these extrapolations are not real, that means this image here is not real also. Actually, it's what is known as a virtual image. In other words, if we were to put a screen here or we were to put our eye here, we would not see an image. All we will see is just like diffused light. We will not see the image of this object. We might see some diffused light from the object, but it would not be the image. But the way these light rays, the actual light rays propagate, it seems as though they came from this point. But if we were to put our eye here, suppose we were to place our eyes here, our eyes can cause these light rays to converge, and therefore we will see some image, and that image we will see will look like it came from this point. I emphasize that this image here is not real, it's virtual. And notice the image is located on the same side of the lens as the object is. Because of this, oh, by the way, it's maybe before we get there, It's located on the same side of the lens as the object is located, and also the size of the image is a lot larger than the object. So you can begin to understand that the magnification will therefore be positive. And in particular, it's going to be even larger than 1 because the size of the image is larger than that of the object. And because the image is located on the same side as the object, we think of this being negative. So dI is going to be negative. So dI is positive when the object is on the image and the object are not on the same sides, but it's negative when they're on the same side. Okay, a more cleaner capturing of this, again, we'll tabulate these ideas. And here we have what we have now is that the second type of image that can be formed is by a convex lens, which means our focal length is positive, and the object is located at a distance that is smaller than the focal length. So the point is that D0 is less than the focal point. So here's our object here. Our object is located at a point that is a lot closer than the focal point. So the image that is produced from such a situation by a convex lens is known as a virtual image. This image cannot be projected onto a screen or a film. And notice the image is located on the same side as the object, the same side of the lens as the object. Hence, dI is negative. And notice its orientation. Look at the orientation of the image. It's upright, which means the magnification is positive. And since the height of the image is larger than the height of the object, this means not only is our magnification positive, but it's also larger than 1. This is the second kind of image that can be formed by a lens. And now we're going to consider the third and final kind of image which can be produced by a lens. In this case, we have a diverging lens. The first two instances we considered were related to a converging lens, a convex lens. This time we're going to begin to talk about a concave lens. So suppose we have our object over here. Notice our object is located at a distance closer to the lens than the focal point or the focal length. And again, using the ray tracing rules, we're going to try to draw our light rays. Because we are at a distance closer than the focal point, we can actually only draw 2 light rays. The third one, which is not needed, by the way, in any case is not needed. We're not able to draw it, but we could draw the 2 necessary ones. And the first one is of the light ray that enters the lens parallel. And by laws of refraction, we know that such a light ray is going to exit so that it diverges. And the way it diverges is indicated here. And then the second light ray is the one that passes through the middle of our lens, through the center of our lens. And remember, this one is unaltered in its direction. So it will propagate right through the lens in this way. Now, the angle, or let's say the angle of refraction for this light ray when it exits as though it came from the focal point of the lens from the other side. That's important. Remember when we drew the light rays, the ray tracing rules of a diverging lens is that they diverge as though they came from the focal point on the other side of the lens. Now, if we were to extrapolate this path and trace it back to the focal point, we will notice that the extrapolated line intersects this middle ray at some point. And the point where they meet is where the image is going to be located. So this object, the object is over here, and the image is over here. This is the principle behind a diverging lens. This is how we recover the image and locate the image as produced by a diverging lens. Okay. Now, what are the properties we can say about the image? Let's put them into perspective and actually tabulate them. Well, maybe before we go there, notice that the image is on the same side as the object. You should be able to deduce what this means for us as far as the distance, the image distance is concerned. And moreover, the object is upright, has the same orientation as the object. The image has the same orientation as the object. And this should also give you an idea about the magnification. And also, the size of the image is smaller than the size of the object. Again, those two facts, those two latter facts, are going to help you understand what we can say about the magnification. And let's go and exactly summarize that. So, the third type of image is formed by a concave lens, which means our focal length is negative. The image formed by a convex lens will be a virtual image. This will be a virtual image, and also the image is located on the same side of the lens as the object, as we've initially stated, and that means di is negative. Notice again, the orientation is upright, hence our magnification is positive. But because the size of the image is smaller than the size of the object, we conclude that the magnification, although positive, hence larger than 0, it's nonetheless less than 1. So another way of stating this is that the magnification is less than 1 but larger than 0. That's another way of stating it. But this idea here combines these two facts about magnification. Okay, this then brings us to the end of our discussion of geometric optics. Initially, we put aside concave lenses in order to introduce the subject, but now it was the fruitful time for us to talk about them in order to have a complete idea of how lenses work. I should emphasize that we've only considered convex lenses and concave. Actually, these are the ones by understanding how light propagates to these types of lenses and how images are formed through these lenses, we can therefore make combinations of these lenses. We could have a planar concave, a planar convex, a lens which is convex on one side and convex on the other side also, or concave on one side and convex on the other side. So concave on one side will look something like this and something like this. This is how your eyeglasses are made. The lenses they have the different radii of curvature. But that's beyond our scope. What we needed to do is to understand how light interacts and how images are formed by these two basic kinds of lenses. And everything else is nothing more than a combination of these. And with that, we conclude our discussion of geometric optics. Thank you.